Hello, this is a talk called Event-Driven Development. It's a kind of a play on all the variants of driven developments that I'm using as sort of a unifying term to talk about a number of different event-based programming architectures and techniques that you may well have come across before. So the idea is to try and fit all these techniques together and try and build a full system. Now, I'm presenting these techniques as a whole to try and fill in any gaps in knowledge you might have. If you've been to a talk on just one of them, like event sourcing, you might have seen it and thought, well, yeah, that's a good idea, but how do I actually put that into practice? So the hope is that you sort of take away from this a little bit more context around how to actually build a system using some of these techniques. It doesn't mean that you have to do all of these things in order to do event sourcing right, but it's sort of to try and help get a bit more context and a bit more understanding of the whole solution. It's important that when you do pick up these, you sort of evaluate against your own use cases and work out which parts, some or all, that you decide to want to apply. So a few of the topics I'm going to be touching upon today, hands up if you've sort of heard of event sourcing. Cool. Quite a few people, that's good. It's a quite key component of this talk, so the fact you've already got a bit of knowledge is good. How about event-driven architecture? Similar number, that's good. So obviously event-driven architecture is exchanging state between microservices, similar to event sourcing. How about this one, task-based user interfaces? Bit of an outlier. Anyone heard of these before? Maybe you will actually have heard of them, but not. You probably understand what I'm going to talk about, but maybe not actually called this before. It's possibly a bit of an odd one, doesn't stand out, but the idea is that instead of presenting a user with a full form to do CRUD on for editing data in a database, you confine the user interface to only request the fields and data that you need for a specific user action. Okay, so you don't update an order and select its new status from a drop-down list and rely on the user to input the correct data for that change. You actually have a specific piece of UI that says, okay, we're going to change the status of an order to closed, so these are the bits of information I need from you to be able to do that. Another one, event storming. Few people having heard of that one. It's not something we're actually going to look at in detail today because it's something you really need to do to get a handle on. But the idea is that it's a modelling workshop that you would do at your company, where you get a bunch of domain experts in the room and a group of developers, and you map out what the system needs to do in terms of what events happen during the process of some business processes. It's really, I mention it here because it's a really good way of actually starting out on actually building these systems. It gives you a good overview of what it needs to look like and how events might fit into the development of your system. So, obviously, we're doing a talk about event-driven programming techniques. We need to know what an event is. All the techniques that we've sort of been looking at kind of related to and part of domain-driven design. Few that are not familiar with this, the idea is to let the domain of your business that you're working in drive the structure and the naming within your code base. This helps when you're talking to someone, your product owner or on the product team, someone in the company that's not a software engineer, but they're an expert at doing what your company does. So they might be an insurance adjudicator. They know a lot about insurance, they don't know very much about software. By using the language that insurance adjudicators use inside your code base, when you start talking about your code base with an expert in your business, they understand what you're talking about, and it facilitates that conversation. Events don't magically appear in a system. An event is only raised in reaction to something. So this could be an input from a user, something happening in an external system, or just the passage of time. Go into more detail. An event is something which has happened in the past. It's a fact about the history of your system. Something has happened. So whenever you're talking about events, you should refer to them in the past tense. For example, order cancelled not cancel order. When discussing them with your business experts, it also kind of helps to use full sentences to describe them. So you'd probably say, an order was cancelled, not just order cancelled. This, again, helps keep the communication going and facilitates faster software development through both sides of the development team and the product team being able to understand each other better. They should be relevant to a domain expert. So someone who knows insurance or knows how your e-commerce system works inside out, if you tell them the name of an event, they should know what you're talking about. It should be terminology they use. If you sit down with one of your domain experts and read out a series of events from your data store, they should understand what's going on. They should know what state that part of the system is in. To ensure that this understanding is possible, we need to avoid technical terms in our events. So you don't want to store on-click events or transaction-committed events. I mean, probably everyone in this room could legitimately store a transaction-committed event, which means it's completely meaningless. It's a technical term. Anyone could use it. Whereas insurance premium calculated, there may be one or two people in the room that might be a useful event for. Those are the kind of events you're looking for, ones that are specific to your business domain. And finally, events must be raised in response to some sort of input. Most common one is going to be input from a user. A user's trying to do something, they'll maybe submit a form, click a button, and that will cause your system to do some processing, and in response to that processing, raise one or more events. Sometimes you get information coming in from an external system, maybe a banking feed provider, and that might cause your system to raise events. Another reason is passage of time. Sometimes you'll also get events raised in response to other events, but you can always sort of trace these events back. So you can say, well, this was raised by this one, which was raised by this one, which was raised by this input to the system. So you should always be able to trace back through your system and say, well, this series of events happened because a user clicked the purchase button. Okay? We're going to start this by considering the first use case, user input, by looking at task-based UIs. Now, computer systems are often modelled around the data they contain. One of the first starting points that a lot of people go is say, right, okay, what does the database look like? What data do we want to store? This data-oriented thinking, kind of like Excel spreadsheet type of thinking, leads to user interfaces for the user, which are designed for data entries. So if you've got a database table, which contains all the order details, you'll tend to have maybe a form which contains all the editable fields for an order. And your staff will sort of sit there and type in data to that form. A task-based UI, on the other hand, breaks away from those data-oriented designs and focuses towards a user interface which looks at the task that a user is trying to accomplish. This means you have a lot more parts of your user interface, but they're much smaller. It makes it much easier to sort of guide a user through a complex task in a series of steps, rather than saying, here's a form, you've got to remember what to do with it. So consider this user interface. Okay, that contains all the information about an order on a single form. You probably access it via maybe an edit list on an edit link on a list of orders, or maybe a search result. Now, if a user is tasked with cancelling an order, they open this form up and maybe they set the status there to cancelled. From the UI, it's not completely obvious that these are potentially required as part of cancelling an order. And it's only going to be the sort of user experience and the user knowledge that they go, well, I'm cancelling an order, so I need to put in the date, I need to put in a reason, otherwise the form is going to throw a validation error. So you're relying on your user to know what to do. If we switch over to something more task-based, you might say, okay, well, we know that we're cancelling an order, so we're going to get rid of that status field. We don't need to worry about the user remembering to select cancelled from the drop-down. It's implicit in the action that they're performing. We can also say, well, the cancellation is taking place right now, so we'll automatically populate in the back end the date for them so that they can't make any mistakes and make it last year or in 3 days' time. And so what we're going to do is ask them for a cancellation reason. And then they click the button, and the back end logic goes away and does some work to cancel that order. Even without training or experience, we're helping a user who's maybe never cancelled an order before get it right. They know what information they need to provide for the system to be able to continue that business process and cancel the order. Everything a company does is part of some sort of business process. By giving your users a basic CRUD-like UI, you're relying on knowledge that's in their heads. Knowledge of the process that might be key and core to your business sits in the heads of your users. Now, that's kind of problematic because users come and go. Okay, you might lose staff, they might go on maternity leave, or they might get promotion, and that knowledge gets lost. You also don't guarantee that it's done correctly every time. Has anyone ever tried unit testing a user? Not very easy, right? So if you've got a core piece of your business logic inside a user's head, you can't test it. And if you can't test it, you can't guarantee that it's correct every time. Task-based user interface isn't revolutionary or new. You've probably already got some forms in your applications that look like the one in the previous page. You're probably already doing this kind of thing. The reason I start this talk off with this UI is because it helps get over a bit of a bump that people often have when they start looking at event sourcing, which is having events that are like order edited, order created. They don't know exactly what was going on with an order because all they've got is this huge form, and there's no way to infer what the event should be from that huge form. If you have a task-based UI, you've got a much easier way of determining that, hey, the user's clicked the cancel order button, they've filled out the cancel order form, we've got some details, we can raise an order cancelled event. This makes it a lot easier to start thinking in terms of events. Events come from users doing actions. Task-based UIs make explicit the actions your users are making. It helps you smooth over that gap into sort of getting into producing events. Okay, so probably the core part of this talk, we'll have a look at event sourcing. It's kind of the core because most of the techniques here work further out as well. So everything you do on a low level, in event sourcing, you can do at a high level on event-driven architectures. At the basic level, event sourcing is the concept of representing state in a system as a series of events which modify the current state. Consider a Git repository. Okay? You've all used Git, I hope, or some sort of version control system. Your first commit, you commit a file into a Git repository. The file sits there, it's there. When you make a change to that file, Git stores the delta. It stores what you've changed. When you change it again, it stores another delta. That means that you can go back in history, you can go back to what it looked like when you first committed it, you can go back to what it looked like before you made your most recent change. When you want to check out the most recent state, it pulls the original copy of the file and applies each of those deltas on top to get to the most recent one. Same kind of thing as event sourcing is doing. So this diagram looks like a traditional relational database model. Might be something you're familiar with, especially if your system doesn't currently do event sourcing. You've got tables to store customer information, an order, and some line items. Whenever your customer goes through the shopping process, adds items to their basket, we're going to row into this table. Whenever they delete something, we delete a row from this table. Edit the quantity, edit the value in that table. Key thing to notice, we're only storing the current state. So if a user adds something to the basket and then removes it, from our system's point of view, we don't know about it. Event sourcing differs conceptually in the fact that you register everything as a stream of events. So customer logs onto the site, we get an order created event. They're starting their shopping process. They add an item to their basket, an item added event. maybe another one, and then maybe they delete one or update the quantity. So we've got all these as events logged in our system. And finally, we get a checkout event when they actually go, make a payment, and place that order. Obviously, if you want to go back and say, well, okay, well, what did our customer's basket look like 5 minutes ago? 5 minutes before they checked out, what did it look like? Oh, it had another item in. Maybe you can gain some insight from that. Maybe you can produce some business analytics that says people are getting to the basket and removing items from it because maybe they've gone over the budget. Okay, so you might be able to use that as business insight to improve your process. Try and get them to buy more. But what does an event source system actually look like? That's a very abstract model, a stream of events. It doesn't really give you any idea as to what to do if you actually want to implement this. How do you build a system around it? It's an issue that is often encountered when going from that sort of theory. Okay, it's all well and good. You've got all these events. How do you make that work? A lot of the terminology is rooted in domain-driven design, and again, if you're not familiar with that side of development, it can be quite daunting to sort of get into this. I mean, the architecture diagram for one of my systems looks a bit like that, which is appreciably quite complex. You don't need to worry about taking this all in now. It's a big, huge diagram, which I'm going to spend the next 10, 15 minutes breaking down into small, bite-sized chunks. Now, I mean, the key thing to take away from the sort of the big overview here is that it's based on a clean onion hexagonal architecture style pattern. You have central in the middle, your core domain model, parts that do the core business logic. Next layer out, you have domain layer infrastructure, orchestration. So making sure data gets routed to the right places, storing and saving data, doing that kind of stuff. And then on the outside, you have everything else. Your infrastructure, you have your database adapters, you have email sending, you have controllers and forms for users to interact with the system. You probably have your test framework sat in there as well. So you've got those nice boundaries, those nice layers to keep your system clean. So, to start understanding of this architecture, let's pick up where we left off on the task-driven UIs. We've got that user interface where we've got a nice little form for a user to cancel an order, and we're capturing the specific intent of our user. They want to cancel an order. So, first step, our user on the left submits that form. Probably doing an MVC type architecture or something similar. So you've probably got some sort of controller or user action handler. That's the first thing that handles it. What that'll do is it'll take the user input, it'll validate that it looks like it's reasonably correct. That means that it'll say, okay, if these fields are required, we'll validate those. Make sure that the user has actually provided a cancellation reason. If you've got any logic that says, well, the cancellation reason is going to be at least 30 characters, it'll do that kind of validation. It's not going to do things like validating, is this order in a correct state to validate? That's not the job. All it's doing is this request that the user is making a valid request? Could we deal with this in the system? It also provides a useful input to our system, a command. So once you've validated all the data, you map it into a very basic object. It'll pretty much just be a plain object with some properties, some getters, and a constructor, a DTO, that represents the action the user is taking, a cancel order action. That then gets dispatched on a command bus. This command bus acts to decouple your framework that you might be using, Symfony, Laravel, Zend, don't mind her, from your business core domain, which you want to keep as far away and decoupled from the framework as possible. Then we have a command handler which subscribes to the bus. That's a sort of a one-to-one mapping with a command usually. And what that'll do is it'll listen to the command bus, and when it receives the command that it is subscribing to, it will do the logic around orchestrating that command. So what it'll generally tend to do is go off to the domain model there, and it'll load a specific instance, a specific part of your domain model. So it might be the order that you're trying to cancel. So it'll load that out of the database. It'll then call some methods on that domain model, which it knows about. So it knows about your domain model and it knows how to interact with it. So it'll say, okay, we're going to call the cancel order method, and it'll pass in some parameters. Providing that the domain model accepts that cancellation and doesn't throw any exceptions or anything like that, it'll pass back to the command handler, which will then save the resulting aggregate into the database. That'll then returns back on success stack, and the controller can send a success message to your user and say, yep, we correctly cancel that order. Obviously, if the domain model throws an error, that'll also get passed all the way back. Controller will handle that, turn that into something that says, sorry, that order's already been shipped, you can't cancel it. Could be something like that. Okay. Inside the model, that domain model, we tend to call this the beating heart of the application. And for an event source system, there's a tendency to arrange it in the following manner. At the lowest sort of conceptual level, you have entities, which are just objects that represent specific concepts. So you might have an order entity, you might have a line item entity. Very similar to how you might think of database tables, but they are PHP models, they're not database tables. And we arrange these entities into groups, which we call aggregates. Now, you tend to logically group these together into things that happen as a group. So you tend to think that an order is going to have line items on it. They are logically associated with an order. And in order to modify anything that is in this logical group, you designate an entity to be the root, the thing that you interact with it through. And so the rest of the system only sees that root entity, which we call the aggregate root. And everything that happens behind that is the responsibility of this entity to coordinate. So making sure that if you're adding a line item, that it's not exceeding the maximum amount of line items allowed on an order, that's the responsibility of the root. Ensuring that you can only delete line items which are part of an order, that's the responsibility of that root entity. Maybe calculating the line total, dealing with tax or shipping costs and things like that, that might be delegated to a sub-entity within the system. But if the rest of the system wants to know about that, again, it talks to the root. This transactional boundary allows you to keep every part of your model separate and tries to ensure small, consistent boundaries within the system. Now, if you remember back to the initial diagram of an event source system, we had a stream of events. Very far back, the one with all the circles on the page. This model is where the stream of events comes from. That aggregate root, that aggregate, is what produces the events. So any time a method call on the aggregate root causes a change within that aggregate, you raise an event. So command handler loads something, and what it will do is it will say, right, okay, go and find all the events that this aggregate has produced in the past from the event store. It will then apply those events to a blank copy of an aggregate, and then it will continue with what it needs to do. So then it will call the cancel order method, which will do some logic inside the aggregate. The aggregate might do some checks, do some validation. It'll then raise one or more events, which it applies to itself. This is quite an important part of what you need to do here, is that you have a validation step, which raises an event, but then that is handled by the same code which is used for loading it. So you're just effectively adding another event on top. There is no validation that happens inside that method. All it needs to do is update the internal state of that aggregate. And if you start putting validation in and that logic changes, you suddenly end up with aggregates that you can't load again, which you don't want. As you consider an event, I'll cover that. So, think back to the big architecture diagram, there are a few things down the bottom left-hand side to deal with handling events outside of the aggregate. So once that aggregate's raised some events, you've stored them in an event store, you publish them to an event bus. And this is where the rest of your system gets to play. You've kept all your consistent boundary and all your business logic and rules inside that model. Now you get to do things that happen outside. So broadly speaking, I tend to break down event handlers into 3 different categories. We have process managers. These they coordinate business processes which happen across multiple aggregates. So if you've got an order and you've got some stock in a warehouse, so you've got something that controls stock in a warehouse as an aggregate, you don't try and edit both of them at the same time. You place an order, that raises an event, a process manager listens to it, maybe raises some more events, which then deals with the work inside the business process of shipping that order out. Go into that in more detail in a bit. Another thing you have down here is called a projection. Now, projections are there to turn a stream of events into a read-only model that your user interface can consume. Again, we'll go into this in more detail in a minute. And then the final thing I've got is this event listener. Now, I'm not going to go into much detail about the event subscribers, but they're for things like sending an email. Things that sort of sit in the infrastructure layer and you don't have much control over. I mean, if you think about it, if you want to send an email, it's very difficult to know if that email has actually reached the person you sent it to. It's sort of like, once you've sent it, you're hoping for the best. So there's no amount of sort of business, you can put a load of business logic and process around that to make sure, have they replied to it? But generally, you're going to say, okay, order confirmation, we'll send it and hope for the best. Sits in one of these. Okay? There's no additional logic to do off the back of it, you just send it and it's done. Okay, so going to go into a bit more detail, looking at projectors and projections. They're a very important concept in event-driven systems as they provide a much more usable model. If you remember back how we load an aggregate out, we load a blank copy and replay every event on top of it. Now that's okay if you have one. If you load up a user interface and you need one aggregate, one entity out of your system, it's probably pretty quick to do that. Okay, you're going to load one up, replay, use it. If you want to do a query across every single order, okay, find me all the orders that are over £1,000, €1,000. That's going to become very expensive, having to load every single one up, replay its events. Is it over 1,000? No, throw it away. Next one, next one, next one. Projections allow you to solve that problem. You create a projection which contains order value into a table, and you can just query off it. And it'll give you the IDs of every order that's over £1,000. So a projection it turns events into state, effectively. That could be database tables, relational ones, similar to what you might be using now. It might be storing something in Elasticsearch to make it efficient to search on. It might be storing it in a graph database. There's lots of different ways you can produce state from projections. They can be eventually consistent. This is a kind of an interesting one, but they don't need to be built immediately. If you've got a projection that's calculating some really big financial end-of-year statement, it's probably going to take you quite a while to calculate all that. You can do it in the background. And you can push events that are happening live onto a queue while you're building that projection in the background, and then it can bring up to speed, and it can do them as a batch job in the background. That's perfectly acceptable. They can be rebuilt. This is probably one of the most important features of a projection, is that you can throw it away and completely rebuild it. This could be due to discovering bad data in a projection. If you've got some bad logic in your code, a bug, and you've got some bad order totals because you summed it up without tax and you meant to do it with tax or something, you can correct it, rebuild the projection, and get the correct data. Obviously, that means that your event store needs to have an ability to pull out events and replay them. That's probably going to be a function that you're going to need to build at some point. Likewise, if you're dealing with events coming from a remote service, which we'll get onto when we look at event-driven architecture in a bit, you need a way of querying that remote service and say, get me all the events that have happened since the beginning of time, because I need to rebuild my projection because I forgot to include a column that the business really needs. I'm going to look at a diagram of what projection looks like. Have that stream of events at the beginning. We pass that through some sort of projection, and we update the. So on the left, we've got a projection which is responsible for keeping track of stock. So this projection, when an item is added to a basket or removed from a basket, this projector updates a count in that that RBDMS table. Equally, if we get some orders going through, we want to have a MongoDB document, whatever, that represents an entire order. So we've got another projector which listens to that stream of events and produces a MongoDB document. Again, you don't have to limit yourself to events that your system has raised. If you're doing event-driven architecture and you're getting events coming in from an external system, you can use those to build projections as well. Okay. The third type of event listener that I mentioned, process manager. As with projections, you'll see these for both locally and remote events coming in. Their role is to track the state of a business process over time. They differ from projections in the fact that in addition to maintaining some local state, which a projection does, they can also feed back into your system by firing off new events, firing off new commands and raising events. Unlike the simplistic listeners, which we don't care about particularly, we kind of want the email to send, but if it doesn't, there's not a great deal we can do about it. A process manager is there to manage both the sort of like happy path when something goes right, you've managed to take a payment correctly from your payment provider, but also what happens when it goes wrong. You try and take a payment, but the card's declined. What do? The process manager is responsible for that process. It can raise a command and say, okay, suspend this order, don't ship it out because we couldn't take payment. So it can raise a command and say, suspend order. And then maybe that'll also raise some events which will trigger a projection to produce a warning in the UI, which then one of your members of staff will see. They'll be able to go in and go, okay, well let's contact that customer and get some updated payment details, and then we can get their order out to them. Okay, so that might be a very basic process that you might have going on. So a process manager handles business logic that stems from events. It's basically a state machine. So for any business process, you receive an event, it causes a transition to a new state in a state machine. At any point in the transition, when we transition, the process manager may decide to fire a new command or raise an event. In my applications, I also have these as event-sourced components, so they actually record all the history of the events and commands that they've received and produced. So you can sort of replay them and play around with them. And so you can see the history that went through a process. Generally, when a process fires a command, it has no way of tracking if it was successful or not, especially if that was fired across a system boundary. So if you call out to a remote system and say, I need you to create this payment, you don't really know what's happened with that. So one thing you can do about that is you can say, okay, well, I'm going to make a call to the payment system, and I'm also going to schedule an event to come back to me in 5 minutes' time. If I receive that event before I've received an event from the payment system saying the payment has been received or declined, then I'm going to do something about it because something's gone wrong somewhere else in the system and that payment request hasn't been processed. So your process manager is actually handling failure by setting timeouts on things that are happening. Be very careful with replaying events and process managers. Projections are really easy. If you replay a lot of events through them, even if you change nothing, you'll get the same projection out, hopefully. If you try and replay a process manager, which is sending commands to payment systems and sending emails and doing all sorts of weird and wonderful extra things, and you replay a bunch of events through them, what's going to happen? You're going to charge your customers again, you're going to spam them with email, and be very careful with replaying events through process managers. Take a diagram. This diagram represents the process of managing a loyalty scheme in a company. As I said, it's a state machine. We've got a couple of states that it can be in: start, single purchase, and two purchases. And we've got commands, the things that the process manager raises here. So imagine you've got a loyalty system, and it says when a user makes 3 purchases within a year, they get a discount voucher. Okay? So at the beginning of the process, they've not made any purchases. So it's a brand new customer, they've not made any purchases. And they make a purchase. So what you do is you set a timeout. You set a timeout and say, wake me up in a year. Tell me when a year's passed. That gets deferred to something in your infrastructure, a cron, which will deal with delivering that message back to the process in a year. In the meanwhile, though, maybe another purchase gets made. And you transition into this state. If another purchase is made, you go into the 2 purchases state. Now, at any point, if that event for a year past comes back, we go back to the start. We reset account, and that's it. Obviously, if they get to the 2 purchases made, we raise a command to issue a discount code. Sorry, if they're in the 2 purchases state and they make a purchase, we get a discount code. Okay, so we've looked at quite a lot of important patterns for developing systems in an event-based manner, but so far the application of these patterns has been at a low level. Okay, single system, internal, within the data layer. Most of these patterns can also be used at a high level. So this high level is often referred to as message-driven or event-driven architecture, and you may already have some features of it in application you're working on if you're using a message queue to send messages between systems. Now, these techniques are best suited to a microservice style application, but there's no reason that you can't use them for decoupling modules within a monolith. It becomes a little bit easier because you don't need a message queue, but maybe a little bit harder because sometimes you end up leaking between the modules. So this diagram represents a possible set of microservices for a ticket booking website. Each of these services is connected to an event bus. It publishes events to it. Other services can then react to these events by passing them into projections or process managers. So our ticketing system could raise a tickets purchased, which the loyalty system subscribes to and proceeds to advance that process of issuing them a voucher. They're not generally, when you do it at a high level, even if you're event sourcing low level, you don't tend to use the same events. If you're thinking about a shopping cart where it's gone item added, item added, item added, item added, you don't want to send all those events out to your shipping system. You only want to send an order has been completed, it's been paid for, and we're ready to ship it out. Send this out, and then the shipping system can get involved. It can grab those events, and it can do something about it. So we're not leaking too much internal knowledge about our purchasing system to the shipping system. You're not also limited to using events to communicate. Sometimes, when you want to invoke a command on an external system, you can make an API call as well. You should do so asynchronously. Send a command, wait for events to come back. That looks a bit like this. This is the final diagram, so we're getting close to the end. You've got 2 systems which look like those big diagrams. Event sourcing in one, all this nice happening inside. Inside the first system, you've got some sort of process which triggers a command that needs to be sent out to an external system. That lands on a command bus. A handler, which will sit in your infrastructure layer because it's making a call outside, handles that command and passes it on using a HTTP RPC call. That's handled the same way as if a user had submitted a form to that service. Controller, command bus, command handler, domain model. Domain model will do some work, validate your request. Hopefully, because it's an automated request, it'll be successful. That then gets some events onto an event bus. An event listener, again, sitting in your infrastructure layer, publishes selected events or rolls up events into a publishable event and pushes it onto a message queue. Finally, the source system has got some sort of anti-corruption layer. That's there. What that's there for is you've got a system that's publishing events to you that you're relying on, and you don't want to be bothered too much if the remote system that you're relying on changes the structure of its events. If they add some new fields, delete some fields, rename some fields, you don't want to have to rewrite whole chunks of your system. That's what that's there for. What you do is you take an event that comes in from an external system and you map it into one in your system. So you map it into an event within the code base that you control. Then, if there are any external changes to those events, all you have to do is change this layer instead of having to change your whole model. Okay? Quite an important layer. Sometimes it'll just pass them through unmodified, but having that layer in allows you to make those changes in the future. And then obviously that fires onto the event bus of the source system, which gets back to the process manager, and then it can actually deal with actually advancing that process. Okay? Right, so that was probably quite a lot of stuff. I hope everyone took a good chunk of that in. I'm hoping that you've got a bit of a better idea of all the sort of architectural pieces that you can put together to form a system. If anybody is still sort of struggling with that, feel free to talk to me. I'm here tomorrow. So I'm quite happy to talk that over with anyone who's interested. So, thank you very much for listening to the talk, and that's my Twitter handle, GitHub, and my blog. If you have a look on my GitHub specifically and my blog, there are some more event-driven articles and things like that you might be interested in looking at. I've also written a event source system which does actually do ticket booking for the conference that I run. You can find that on the GitHub organization conference tools. Take a look at some of the code in there and see how it actually fits together and actually builds a system which is in production and working and sells tickets to conferences. So if you want to actually have a look at some code, that's there. Right, thank you very much.